Yeah, good morning. Welcome to the first cases session. So, my name is Oliver Brinkman. Yeah, not Geronimo. And we changed the session because, yeah, the train, of course, the German train, have a delay. And yeah, I just took over the BIOS. And yeah, and it's my pleasure to announce the first presentation, because the first presentation is actually a best paper candidate. And the first presentation is about let coarse-grained resources be shared, mapping entire neural networks on FPGAs. And the presenter is Zhuanghan Wang, and he's a third-year PhD student from McGill University under supervision of Professor Christophe Dupas. And his current research focuses on parallel synthesis of neural network architectures, accelerators, and he's also interested in topics related to compilers, hardware design, and machine learning. So, the stage is yours, and you have the mic.
Okay, yeah. Can you hear me? Yeah. Okay, so hi everyone. Thanks for coming to my talk. So, first of all, we all know machine learning is very popular right now. We have lots of applications. For example, we have ChatGPT, we have object detection, text to image. So we have so many applications, but they all require lots of computations. For example, neural networks for object detection, it uses billions of multiplications. So that's the reason we need efficient hardware. So what are the options? So here we have CPU, the very basic one. It's easy to program, but it's not very efficient. We still have GPU. It provides more parallelization, but it's a bit harder to program. And we still have FPGA and ASIC. So they are mainly for hardware design. So you need to write the hardware description language for them. That can be a bit more difficult, but you design specific hardware for them, so it can be very efficient. But the problem, especially for ASIC, is once the hardware is tailored, you cannot change anything anymore. So that's the reason we are focusing on FPGA right now. It provides us a certain degree of reprogrammability, and it can be efficient. So the problem we want to solve is how to make writing the code easier for that. But why this is the issue? So let's take a look at machine learning side. So this figure, the x-axis is the years and the month, and the y-axis is the number of publications. So it shows the trend of machine learning papers per month grows in exponential way. Why this is a problem? This is because hardware design is still very time consuming. So the developers have to work very hard to catch up the trend. So that's not what we want. So that's the reason we want to automate the process. But before doing that, we still need to handle the issues in hardware, especially for resources. So let's take a look at the example of VGG network. So it uses billions of multiplications, and suppose we want to fit 3 layers into a single FPGA device. So a device only has very limited amount of resources. For example, it has 15 multipliers. So how should we do that? So as soon as we can fit 1 layer into the device, but this layer already uses most of the resources, then we will encounter a problem because we cannot directly fit the second layer because there's no resources. Then how to solve this? Actually, this is very easy. As soon as these layers are in the same shape, we can just make sure they are using the same set of resources. But the problem can be a bit trickier if we choose 2 layers that are in different sizes. Because for a hardware, you must make sure the input are always in the same size. So we need to do some effort to maintain the data size. But how do the existing tool handle this problem? So let's take a look at the Intel OpenCL example. So we tested this on Area 10 FPGA, and we first define a function. It's called memo. So it's for matrix multiplication. And we have a kernel main function. We will call the memo several times. So first, we call the memo first time. So we have a DSP efficiency. DSP usage. So DSP is mainly for multiplication. And this number is just for reference because we will call the function second times. So you can see the number of DSPs doubles. So it looks like the tool does not handle sharing automatically. And if we call the function 3 times, then we have a trouble because there's no enough resources. So this is the motivation. And then we want to somehow solve this problem with functional approach. And you might wonder why we want to choose functional. Because neural networks are functional. So here we first define a fully connected layer. So it takes an input and a weights. So in functional programming, when you have a variable like this input and weights, they are always will type defined. So we always know the size is a 1D array and the weight is a 2D array with a certain size. And what we want to do with fully connected is that we want to multiply input and simple weights. So then we have a map and it takes weights as the input. And then we will do dot product inside the weight. So here, the next part is for the dot product. So first we group the input and each small weight together, do element-wise multiplication, and then do summation with reduce. So you can see it's a combination of map and reduce. Of course, we can do something very similar to the other layers, for example, with regression layer and activation layer. And with this, we can build a neural network. So this is just an example. We are coding fully connected layer twice, activation layer twice, and a regression layer. So we have a simple architecture like this. We will see this later. And our framework will turn this into hardware. So how does it work? So let's take a look at the example, fully connected layer. I have color-coded the imported primitives. So in our framework, we will turn each primitive into a hardware template, something like this. So you can see here, we have an outermost map. I have marked it in red color. So it takes weights as the input and then do dot product inside there. So you can see how does this work, how does this flow work. And with this idea, we know how to turn functional primitive into hardware. Then we would like to introduce the idea of sharing. So here we are using some standard primitives, but they are from functional programming. They are mainly for software, but here we want to combine them with the concept of hardware. So first of all, we define that. That is the most important thing for sharing. So we define a value underscore. And for this example, we define x equal to 3 and want to reuse this x several times. And the code on the right is C counterpart. And after that, we have lambda. Lambda is to define an anonymous function. So here we have a parameter x, and we want to use this x twice, for example. After we have a function, then we want to use that. So in functional programming, we have funcall to use the function. So here we call the function once. Of course, you can call it several times. So you can see the idea of functional approach here, and we want to turn these primitives into hardware. So let's take a look at the details. So first of all, we have to define a function here. So it's called +1 func. +1 func is to add every element in an input by 1. So here we have an example. So suppose the input has 3 elements. So this +1 func will process each element one by one, just like this animation. So you can see data comes in a streaming way. And what about if you want to do the function twice? So without that constructor, there's no concept of sharing right now. So what we can do is just to define the function twice. So you can see we have function 1 and function 2 here. Suppose we have input with 2 elements. So the first function 1, will process the first element. And after that, it is supposed to process the second element. But at the same time, function 2 has already received the intermediate result, so it can also process that. So you can see there's a pipeline here. And after that, function 2 finish all of that. Of course, it works, but the problem is there's no sharing. Suppose this function is very expensive, then you can no longer fit 2 functions inside a single hardware. Then that's the reason we want to introduce that constructor here. So we use that constructor with the function. So with this, it will introduce an arbiter and a pair of mux and demux. And the number of ports to mux and demux depends on number of function codes. So here you can see there is a feedback path from the output of funcall 0 to the input of funcall 1. And actually, there is a problem. So let's take a look at the example again. So here we have example two elements. First, the arbiter will grant access to function 0. So function 0 can process the first element. But after that, we will have a problem because function 0 is supposed to process the next element, but function 1 has already received intermediate array, so it is supposed to process that, but it has no access to the function. So the data has nowhere to go, and the circuit finally gets stuck. So you can see the problem. And actually, we define this as a complete. So it means there are two function codes. They are calling the same function, and they have the relationship of data dependence. So how to solve this problem? So actually, it's very easy. We just want to make sure these function calls are not happening at the same time. So here we insert a buffer in the feedback path. So here, suppose the after the function 0 finish, the first element is stored into the buffer, and so does the next one. After that, the arbiter will grant access to the next function code. And the next function code, function 1, will finish all of that. So you can see the idea here is simple, but the problem can be a bit complex if we have several functions. So let's go back to the example of neural network. So here we have seen this before. So we have two fully connected layers and one regression layer and two activation layers. So the computation is something like this. So here for regression layer, you can see we are going to multiply each input by a weight and do summation. So it's actually a dot product. And for fully connected layer, you can see we are repeating dot product several times and the output is vector. So it's actually a matrix vector multiplication. So we can define function in a three different way. So here is an example. So first we define dot product function, and it's called by regression layer. And we also have another function, it's called MBO, it's for matrix vector multiplication. So it is also calling dot product. And two fully connected layers, they are also calling this MBO. So you can see the structure can be hierarchical. And here we also show you the simple expression. So here we define the functions with that constructor. And you can see in every mode bound, there is a function code, and the other 5 function codes are under the band scope. And with functional approach, we can easily turn the expression into a tree. So here I show you two subtree. So the first subtree is for MV mode, and the other subtree is for the band scope. So without this subtree, how should we find out the completes? So here we will show you the steps. So here first we build a graph for each one. So you can see MV mode has only one node because we only have one function code. But for main scope, it has 5 nodes because there are 5 codes. So here we'll go through function by function. So first, let's start with activation function. So you can see activation function is called by function code 5 and function code 3. And you can see function code 5 somehow depends on the ratio for function code 3. So there is a relationship of data dependence. So there is a complete. You can see we draw an edge between node 3 and node 5. And let's move to MV mode. So we have function 4 and function 2 here. So they are also accessing the same function, and one is also depending on another. So there's a complete. But the next one is a bit trickier. So here we have dot product function. So it's called by function code 6. And in another scope, we have function code 1 is also accessing this function. But you can see function 1 is under the scope of MV mode, but MV mode is called by function code 4. So we can treat it something like function code 4 is actually calling dot product function. And you can see function code 6 is happening, it's used the ratio from function code 4. So they have the relationship of data dependence. So there is a complete. And we can also apply the same rule to function code 6 and function code 4. So you can see we find out all the edges, but what do they mean? So actually, this concept is very similar to interference graph from register allocation in compilers. So in register allocation, we want to make sure a register is not used twice at the same time. And here, we want to make sure a function is not used twice at the same time. And if we want to remove a complete, then we just need to insert a buffer. But for example, if we want to do something different, we just don't care about the word, we insert buffer everywhere. Just like this, we insert buffer every 2 functions. It can definitely solve the problem, but that's not efficient. Why? Because you can see we have function code 2 and function code 3. They are using different pieces of hardware. So they should not have the issue of conflict. So you can see that's not efficient. Then how do we do this in a more efficient way? So let's go back to the figure again. And here we introduce the idea of the code sequence. So it means one function call happens right after another. So for example, function call 3 is happening after function call 2. And here we are using a greedy way to find our place to insert a buffer. For example, we can put a buffer between function call 3 and function call 4. So it means everything before function call 3 and everything after function call 4 are separated. So these 2 sides will have no conflict. So for example, function call 2 and function call 4, there's a buffer between them. So there's no conflict. Function call 3 and 5, there's buffer, so no conflict. The same as 2 and 6. So you can see actually what we are doing here is that we try to use greedy way to find out the place which can remove most of the edges. And we still have one edge between 6 and 4. So we just need to find a place to insert a buffer, maybe right before function call 6, then we can solve most of them. And here is the architecture. So you can see we only need to insert 2 buffers here. And why this matters? That's because a buffer can be anything. For example, it can be your memory space. So it means maybe you need to send your data out of chip to somewhere else, and you introduce extra transfer time. So that's not what we want. So that's the reason we don't want too many buffers. So here we show you the example, but they are all in the same sizes. But what about if we have a neural network and there are 2 layers? So here we have 2 fully connected layers. They are in different sizes. The first one is size 2, the second one is size 4. So here, suppose we pick one of the layer as the function. So we use size 2. So for the first layer, we don't need to do anything because the size is matched. So we just need to call the function. But after that, for the second fully connected layer, we have a problem because right now the size is 4, but the input size for the function is 2. So we need to do hiding. We need to separate the input. So here we process the first part, and after that we process the second part, and then do summation and finish all of them. But you can see it introduced more steps. But what about if we use a large input size? So for example, we use 4 as the size. But the problem for the first layer is that it only has input 2. So we need to do padding first and then call the function. But after that, the size is matched, so we can directly call the function again. But you can see the problem here is that we have many redundant operations. So it's also so there will be a trade-off between the choices of your size. We will see this in evaluation. So for our experiments, we have an Area 10 FPGA, and it is connected to a host server by PCI Express. We consider the data transfer time across this interface. And here we use BGG and TinyYOLO as an example because they provide different sizes for different layers. So for some layers, they are very wide, and some layers, they are very deep. So it's a good example to show how we can do exploration. But before we are doing that, let's take a look at the issue of sharing. So here we define a score called DSP efficiency. So so we have a number of operations for your application divides the number of runtime and your number of DSPs. So actually this score tells us how close to the performance upper bound. Because if you have an efficiency like 100%, it means you have already saturated your computation. But if you have something like 20%, it means, oh, we still have something to improve. So here we use an example of 2 layers from BGG network. So first of all, suppose we do not do sharing, we will have problem because a layer will lose most of the resources on FPGA. And the next one is that we can do sharing. So we just make sure these 2 layers, they are using the same set of resources. So that works fine right now. And another choice is that we can do partition. So here we reserve half of the resources for one layer and another half for the second one. But the problem is that if we have an input image and feed into this accelerator, so first layer will process the image, and the second layer will have to wait for the second layer. So you can see it's also not quite efficient for this use case. So that's the reason we are focusing on sharing for now. And for next part, we can talk about the size. So here we pick layers from VGG network in x-axis, and the y-axis is the runtime. And we have 4 choices of size. So for example, we have a convolution layer 4. So here we try this size. So if we choose a small size, it means we need to have more steps. So it might introduce more data transfer between your FPGA and the memory. So it's not quite good. But if we pick a large size, it means there will be so many redundant computations. That's also not what we want. So that's the reason we pick a middle one, like 8x8 for this case. But how can this help us? So if we have another layer, they are very similar to convolutional layer 4. For example, layer 5, it has very similar feature compared to layer 4. So we can predict the performance model for convolution layer 5 is almost similar. So let's take a look at all of them. So here you can see layer 5, it also have the same feature. So we need to pick a suitable size instead of the very small or a very large one. So for comparison, we also compare with some other work, and they are all using Area 10 FPGA, and they are using OpenCL manually. So what I mean is that they have to handle sharing and scheduling everything by hand. And for us, the performance, you can see our performance for VGG network is better. So operation per cycle is for the speed. So the higher, the better. And we also compare with YOLO network, so we still can have a better performance. So for the conclusion, neural networks are perfectly fit with functional programming. And that constructor is the most important one for us because it expresses the opportunities of sharing. And for future work, we will further automate the process because the users still have to define their own function. And we will further support PyTorch front-end because we want to have more access to the latest model. And some of the users might not have the knowledge about functional programming. And that's all. Thank you very much.
Thank you very much for your presentation. Probably I will start with the first question. How do you deal with memory access? Do you have specific operators to access memory?
Oh, yes. So we do not have time to show. Just for this example, you can see we have web, we have input. So actually, we have the memory operation. It's called read. So it will read for example, we read one from the memory space, and our compiler will allocate the memory space somewhere else.
But if you have to access external memory, then you have to wait longer than if you have data already available in FPGA. Do you consider that already?
Oh, so do you mean the memory on FPGA or?
Yeah, both. You have both options, of course. Yeah.
Yeah. So for our experiment, we assume the data mainly comes from your host. Mm-hmm. So you know the host can store lots of data. So we assume the data comes from that. So and our accelerator will request the data from the host. So that's how we allocate the data.
Okay, but then you have to schedule that as well.
Yes,
when data
right.
is available. Any other questions? Yep.
Thank you very much for the presentation. So how would you compare your approach to some of the existing approaches which provide Python-based wrappers, which also creates an array of a systolic array kind of implementation where the resources are reshared and the user has to just create a Python wrapper kind of thing and then just simply execute a simple Python wrapper.
You mean compare with systolic array?
Yeah, for example, there's a framework, a recent framework with the name Tensor AI, which, for example, creates a systolic array-based implementation of processing elements. The user can then reuse the same resources multiple times for different type of nets. So I was just wondering, how would you compare your implementation with those implementation, which are systolic array-based implementations?
Oh, yeah, it's a good question because we have, does the framework also use high-level synthesis? Because the reason we pick the comparison is based on they are also using the high-level synthesis framework. So they are using the same hardware because if we are comparing under the same hardware, the comparison may be more meaningful.
One last question.
So there is a lot of work on ReRAM-based processing and memory accelerators for deep learning in general, right? How do you see fusion being conjunction that line of work? Is it synergistic, or do you think it's orthogonal? Can you comment on that?
Which framework?
ReRAM-based processing and memory accelerators for.
Oh, it's a hand designed accelerator or accelerator generated by high-level things. I just want to compare because our approach is based on high-level synthesis. So our comparison for now is just to compare with maybe OpenCL synthesis or C synthesis. So we still not yet consider this case, but it's a good comparison point.
Yeah, thank you very much again for the speaker. If you have more questions, please go to the posters just in front here of the lecture. So let's thank again to the speaker. And now the second presentation will be given by Halima Bouzidi. He is with Polytechnic University of Haute-France. And Halima Bouzidi is a third-year PhD candidate in computer science at the University of Haute-France, and she received her master degree in 2020 from a higher school of computer engineering in Algiers. Her research interests encompasses the design, automation of neural networks on resource-constrained hardware devices, as well as neural networks computations mapping on MP-SOCs. So, the stage is yours.
Thank you for the introduction. So, hello everyone. And today I'm delighted to present our work, Magnus, a mapping over graph neural architecture search framework for heterogeneous MP-associated problems. So graphs are all around us, and they are the main modality that we see from our environments. This is because real-world data are often defined by their interconnections to other things. Considering related objects together, their relationships can be naturally expressed as a graph, where nodes are the objects and edges are the different connections between them. However, graphs are irregular structures of data that require a smart processing, and this is where graph neural networks come into the scene. So a GNN captures semantic features from a graph by aggregating neighboring nodes embeddings and combining them intermediate features. This learning paradigm has enabled many of today's applications, such as social media recommendation, chip placement and design, scene graph generation, and drug discovery. The application of GNNs has been recently extended to encompass the world of computer vision. So images are a regular grid of pixels that can be also transformed into irregular dense graphs. This transformation involves splitting the image into patches of similar sizes, then grouping similar and neighboring patches together, then creating the graph image by adding the edges also. Then we have the GNNs that will operate on the generated graph image by performing a series of aggregation, combination, and features transformations. So for instance, in the graph processing layers, we have two main operations. We have the aggregation part, which is more responsible for communicating the embeddings of the neighboring nodes. And we have also the combination, which is a fully connected layer with an activation function to scale the features. We also have another component, which is the feature transform layer, which is an FFN module or feed-forward networks to enhance the features diversity, especially for visual-related tasks. So in the meantime, we are witnessing a rapid growth in neural networks and GNNs as well, making it hard to run them on edge computing devices. Specifically, neural networks are getting more and more complex every 2 months, exceeding the hardware scaling capabilities of Moore's law. On the other hand, hardware specialization is an interesting direction by designing specialized AI accelerators for each emerging application. However, we have here the physical limitations that is a real burden as we are approaching the end of Moore's law. So the question now comes on how can we efficiently execute the emerging GNNs on existing heterogeneous NP associates. So before answering this question, we need first to understand the workload characteristics of GNNs. Compared to classical and typical neural networks, the particularity in GNNs are the graph data representation and this interplay between aggregation and combination bias. So typically, the graph is represented as a sparse adjacency matrix on which the aggregation will be operated by retrieving neighboring nodes and aggregating their features. Then we have the combination that will follow up by taking the results of the aggregation and performing dot products to scale and reduce features. So if we look at these operations computationally, we have the aggregation that can be seen as a multiplication between a sparse and dense matrices, whereas the combination is a multiplication between two dense matrices, which is the typical GEM operation. Also, these two operations will be invoked multiple times within the GNN network, creating what we call a multi-phase computations that will also lead to irregular data access and patterns, especially when we have like a high sparsity in the adjacency matrix. So in light of these observations, we can now summarize the following challenges. First of all, in existing NP-SoC accelerators, the general purpose accelerators, for instance, GPUs or specialized ones, for instance, NPUs, are not designed or tailored to handle this irregularity within GNNs. Second, the hardware physical limitations prevent integrating new, heavy, and highly graph accelerators onto existing NP-SoCs. And third, the field of GNNs is rapidly evolving, maintaining the flexibility to new of the hardware accelerators to new GNN generations really hard. So now we have another question on how can we beat the curse of irregularity by optimizing the design and the mappings of GNNs on existing NP-SoCs. So existing NP-SoCs comprise a diverse set of computing units, mostly heterogeneous, and have different hardware characteristics. For instance, on the NVIDIA HGX Xavier, we have the GPU, which is latency efficient, but energy hungry, whereas the DLA, which is energy efficient, but slow compared to the GPU. So if we consider the typical deployment option of taking an entire GM application and deploy it on the GPU or the DLA, we have two drawbacks here. First of all, we're going to compromise one performance to another. For instance, we're going to compromise the latency over the energy or vice versa. And also, we are not making a full and efficient use of all the hardware accelerators that we have at hand. We can now consider another interesting option, which is the distributed computing over different computing units. But in this case, we're going to need to think about two main things. First of all, we're going to need to think about the model splitting options, whether we are going with a pipeline fashion or data parallelism, and at what granularity we're going to do the mapping. Also, we're going to need to think about the constraints on the hardware and the SoC side. For instance, how many CUs we're going to consider, how can we manage the memory sharing, the communication, the memory contention also, and whether the framework or the software framework support certain operations or not. And by combining the two, we're going to find ourselves against a black hole of options, constraints, and decisions to make, which also approaches the problem to a design exploration one. Now, to put things in a more complete context, we give a motivation example in here. We fix the GNN architecture and we vary only the graph layer operation, specifically the aggregation one, to 4 variants, to MLComp, HComp, GENE, and graph stage. And we compare the results against the accuracy, latency, and energy consumption. So by seeing the first or the top figure in here, we can see that there is no clear winner among all the graph operations. For instance, the HComp is the more accurate one among all of them, but less efficient compared, for instance, to the baseline MLComp. We have also the GENE operation, which is more efficient, but less accurate compared to the other alternatives. Second, we also compare different deployment options. For instance, we take the same GNN architecture and we deploy it on the GPU only, on the DLA only, and on another distributed mapping option. So we can make here 3 main observations. First of all, the GPU only deployment is the option with the fastest execution speed. And the DLA only deployment is the option with, or we can say it's the most energy efficient alternative, whereas the distributed option over the DLA and the GPU is the one that provides the best compromise between latency and energy. More importantly, by combining GNN graph optimizations and deployment options, we can also have a better trade-off in terms of accuracy, latency, and energy consumption. So our final research question is now, how can we better characterize this combined GNN architecture mapping design spaces to obtain better performance trade-offs? So now we consider a vision GNN architecture which comprises n computing blocks, and each block can be either a grapher for the graph processing or an FFN module for the feature transformation. Then we define a mapping vector M to assign the workloads of the computing units over the different computing for the computing blocks over the computing units that we have on the MPSoC. Then the overall performances of a single mapping vector, that means the latency and the energy, are characterized on a layer-based basis. That means that for each layer, we characterize the overhead of the computations and the communication. So the communication overhead arises when we have a transition between a computing unit to another, because each computing unit has its private memory, so it needs to fetch input data from the VRAM, do the computations, and then writes back the results. So the problem that we have here is a multi-objective optimization problem to find the best, we can say, mapping vector to assign the GNN workloads on the computing units of the MPSoC in a way to find a better balance between latency and energy consumption. On top of this mapping problem, we add also a graph neural architecture search to scale the GNN architecture. So the aim of the NAS here is to find better, we can say, architectural parameters of graph operators and components by searching through a predefined search space. So combining now the graph NAS problem and the mapping problem, we have an overall co-optimization problem where we are searching for the best pairs of GNN architectures and their mapping on the computing units of the MPSoC. So we have basically here three main objectives to optimize: the accuracy, the latency, and the energy consumption. So now to characterize the design landscape of the GNN architectures, we propose in our work a novel design of SuperNets based on the state-of-the-art VIC model. So a SuperNet, for recall, is a sort of hyperpyramid network that comprises multiple architectures and alternatives for a fixed macro architecture. So for our case, we fixed the macro architecture to the state-of-the-art VIC model that comprises a STEM module for the image to graph transformation. We have also a sequence of VIC superblock for the graph processing and feature transformations, and a prediction model at the end for the classification. So then we define a kind of a search space for the microarchitecture of the superblock by making it dynamic in a way, by varying different architectural parameters. For instance, the depth, how many layers of grapher and FFN modules are within the superblock. We also vary the graph operation, the aggregation specifically to the four alternatives that we discussed before. We vary also the number of hidden components in the combination layer. And we also make some layers optional, for instance, the graph pre-processing in the grapher module and the FFN module entirely. Then to search or to make best of both worlds of the GNN graph architectures and also the mapping strategies, we propose in our work a novel framework with two-stage evolutionary search optimizations to co-optimize the GNN design and also the mappings on the MPSoCs. So our framework Magnus employs pre-trained SuperNets in order to synergistically design GNNs while also searching for the optimal hardware mapping on the different components that we have of the SoC. Also, because if we combine the two search spaces of GNN architectures and the mapping strategies, we're going to end up with a large search space hard to explore without compromising the optimality of the final results. So that's why we propose in our case an hierarchical design space exploration by selecting in an efficient way some expensive and promising experiments for the two search stages that we have. So now let's break down the components of mappings. First of all, we have the auto optimization engine, which is the GNAS or the GraphNAS part. So its mission is to search through the supernet, the pre-trained supernet, in order to identify accurate and energy or hardware efficient subnets on the distributed mapping settings. So we're gonna start with some search space defined by the supernet that we have, and we're gonna iterate over it in order to sample different GNN architectures. Then, because we sample multiple GNN architectures, so each one of them will undergo a mapping optimization through the inner optimization engine that we're gonna discuss later. And after that, after getting the results of the accuracy, latency, and energy measurements, we're gonna compute a fitness evaluation function based on the Pareto ranking algorithm in order to assign, we can say, an optimality score for each GNN mapping pairs. Then based on these scores of optimality, we're gonna rank our results from the best to the worst one, and we select the first top quartile to generate the next generation of the evolution with some variation search operations that are called crossover and mutation. So we're gonna iterate over this process multiple times until reaching an optimization budget. For the inner optimization engine, which is the second component, so we're gonna run this engine for each sample GNN by the previous outer optimization engine. So the mission here is to search through the space of mapping vectors in order to identify ideal mapping strategies of all the GNN workloads on the computing list of the MPSoC. We also add a support for DVFS, or the dynamic frequency scaling, in order to scale the operating frequencies on the components of the SoC to have more, we can say, energy gains. And then based on the measurements of latency and energy only, because the mapping will not impact the accuracy of the GNN, we're gonna compute a fitness evaluation score as a weighted product of latency and energy normalized by the maximum values. Then based on these scores from the fitness evaluation, we're gonna also rank the results from the best to the worst and take the first, we can say, top quartile to generate the next generation of evolution with mutation and crossover. We're gonna also iterate over the process until reaching an optimization budget, and at the end, we're gonna have a Pareto front of optimal mapping vectors. So now we're gonna move to the evaluation part. Here we have some details about our joint source spaces for GNN architectures, mapping, and clock frequency. So we vary the clock frequencies, for instance, on the NVIDIA Xavier EGX, on the CPU, on the GPU, on the DA or the external memory controller, and also on the part. For the training of our super network, so we train them on 4 data sets for image classification on the Cypher 10, Cypher 100, Oxford Flowers, and time imaging. And the training took from 2 to 3 GPU days. Then for the hardware experimental settings, we use 2 settings in order to evaluate the mapping strategies that we are proposed. We use the NVIDIA Jetson Xavier, which is a real MPSoC platform, and we also use Maestro, which is a prediction or a cost model for hardware evaluations to emulate the case of an MPSoC varying the data flows. So for Maestro, we use the native data flows without any changes, without any further optimizations. We also fix the clock frequency for it. All right, so now we're going to show the results of our framework regarding the multi-object optimization efficiency. First of all, we show how the scaling of the GNN architectures provide better results than the baseline. So in here, we take the results of the auto optimization engine on the one device mapping only, on the GPU only, and on the DLA only mapping. And we can see from the comparison of our Explore GNN architectures compared to the baseline that we have energy efficient models compared to the baseline. So our update Pareto front on the bottom is, we can say, more energy efficient than the models on the baseline on the top, with the same accuracy level on the Cypher 10 dataset. So now, if we look more at the results of the distributed mapping, and in this case, for instance, we combine the results from the outer optimization engine and the inner optimization engine. We group them also by 2-point error scores. And in this case, we can see that the result that we have boosts further the energy efficiency of the GNN architectures if we consider distributed mapping. For instance, we have a 3.2 energy gain compared to the baselines noted by the extremes points on GPU only and on VLA only. Then to emphasize more the efficiency of the optimization, we provide here some results on the hypervolume. So the hypervolume is a metric used to assess the space dominated by the parity form in the multi-objective context. And compared to performing like a typical NAS without any distributed mapping, we can see that Magnus provides like more than 5% of dominance over the one-to-one mappings. And also we provide some statistics about the result that we have, especially on the parity front. So in here, we can see that more than 23% of mapping strategies located on the parity front are distributed mapping options and not one device mapping options. So now let's look in details on the results that we have, or the optimal models that we got from our two-stage search framework. So first of all, in here, we compare the results regarding the accuracy, regarding latency, energy, and also some parameters. So for instance, over the 4 data sets, over the Cypher-10, Cypher-100, Oxford Flowers, and Tiny ImageNet, we can see that our framework has been able to identify accurate, we can say comparable to better models in terms of accuracy. Then by adding the distributed mapping option, a latency or a speed up of more than 2 times in latency, and we have also a 1.6 energy gains compared to the baselines. Then if we look, for instance, at the parameters that we have on the GNN architecture, we can see the diversity of the graph operations, for instance. So like if we consider, we can say a hybrid scheme of incorporating different graph aggregation layers, we can also have more interesting results because the framework now is aware of how to place, we can say, the graph aggregation layers at different stage of the GNN network. And if we look also at the ratios of how many workloads are assigned to the GPU or to VLA, we have a certain trade-off and a certain balance between them, like without just deploying all the workloads on one computing unit over the other. So we also, our framework has made use of, we can say, the hybridity of the different computing units on the NVSS. So now we look at the details of the mapping strategy of one GNN architecture picked from our results in here. So we give here further comparison with another state-of-the-art approaches that also consider this distributed mapping over the different computing units of the NVSLC. Specifically, this approach set some constraints on the number of transitions between the computing units on the NVSLC. However, our approach is a non-constrained search, so we don't set any constraints on the number of transitions, and we let the framework figures out what are how to assign the workloads regarding their computation and memory requirements. So we can see that our unconstrained search within the inner optimization engine provide we can say effective mapping, especially in terms of energy consumption, because for instance, in our mapping strategy, most of the grapher layers are assigned to the GPU because they require like a lot of computations compared to the feature transformation layers, whereas the other layers are located mostly on the VLA. So on the DVFS support, so we also incorporate the search of the optimal clock frequencies regarding of given like a certain GNN architecture and the mapping strategy. And we can say that our search DVFS provides better balance in terms of latency and energy consumption compared to the other one, like the MINAMP. It's the DVFS policy that minimizes all the clock frequencies on all the components. The MAXAMP is the one that maximizes all the clock frequencies, and the default one, it behaves like in a dynamic way. So our search one will prevent some latency, like unpredictable latency values, while also minimizing the overall power consumption. On the scaling capabilities of our framework, we have evaluated Magnus like on two different macro architectures of GNNs, the isotropic one and the pyramid one. So the isotropic macro architecture GNN maintains the same graph size across all the layers of the GNN, whereas the pyramid one will reduces the size of the graph as the network difference to account for, we can say, the multi-scale features of vision data. And we can see that Magnus also scales on the pyramid GNN. For instance, if we compare the two results in here, we can see that in the isotropic case, we have like uniform like mappings distributions also offer the energy and latency. Whereas when we go to another complicated, we can say, GNN architecture, which is the pyramid one, we have more convexity of the optimization stage. So if we, for instance, consider like just a mathematical formulation to assign the weights or the ratios on the GPU and DLA, it will not work. It will not work for the second case because the problem is more complex. And also, like if we consider the mapping on just two computing units, it seems like a really simple problem. So in this case, we also increase the number of computing units with the Maestro experiment. And we can see, and also we vary the mapping granularity. We compare the block ways and the layer ways mappings, and we can see that if we go with a finer grain mapping strategy with the layer ways mapping, we're gonna have like an interesting trade-off in energy and latency, and we're gonna spot, we can say, this area of the trade-off really quickly compared to the block ways mapping. So to summarize, in this work, we incorporate the case of graph neural networks and their efficient execution on MPSRCs. Specifically, we tackle the case of vision graph neural networks. We also provide a distributed mapping strategy, discuss the pipelining mapping over the computing units of the MPSRC. We propose to investigate we can say, the two search spaces of GNNs and mappings. We propose Magnus, which is a two-stage framework for co-optimizing GNNs and their mappings on MPSRCs. And like according to our results, we can have like more gains in accuracy and energy consumption by being aware of this interplay between GNN architectures and the mappings. So thank you.
Yeah, thank you much for your interesting presentation. Any questions from the audience? Yeah.
So thanks for sharing. So I think you're doing DSE considering the mapping parameters as well as the neural network parameters. So it's like you fix the hardware parameters, you fix the hardware platform. So I was wondering whether the results will change after you change the hardware platforms, use other GPUs and other DLA combinations. Have you done any research on this? Thank you.
All right. Thank you for your question. That's a good question because in our case, for instance, we suppose like the hardware configurations are optimal. But like if we go for another hardware parameters, for instance, another GPU or CPU, it depends on how contradictory are the computing units between them. Like for instance, in the case of the Xavier, we have the GPU, which is always latency efficient, and the DLA, which is always energy efficient. So we have this contradictory nature, which also gives a motivation for the distributed mapping. But if we go for another hardware settings, like we can have some changes. But in our case, we don't investigate any optimization for the hardware configurations. We suppose that the hardware is really steady at this stage.
Okay, I would like to go ahead because we're running out of time. Thanks a lot for your presentation. And Please drop in a poster for asking further questions. Let's coming to the third presentation, and the third presentation is given by Salma Afifi. Salma is a PhD student at Colorado State University, and her research interests include artificial intelligence and machine learning, hardware accelerators, silicon photonics, and in-memory computing. So Salma, the stage is yours.
Okay, thank you for the introduction. I'll be presenting our work GHOST, which is a graph neural network accelerator using silicon photonics. So for this is the outline. I will start with a quick introduction on graphs and graph neural networks. I will then dive into silicon photonics and explain how we use it to perform the graph neural network operations. I'll then present our proposed solution, which is GHOST. Then I'll show the experimental results and finally end with some concluding remarks. So first of all, what are graphs and why is dealing with graphs such a non-trivial challenge? This is mainly due to their very unique structure, which is very different than regular structured data, such as images, for example, which restricts us from using traditional deep learning algorithms such as CNNs, for example. And if we look around us, graphs are everywhere. We see them in social networks and recommendation systems, in the bioinformatics area. And just to give you like more in-depth sense of why we need to process graph data, if we focus specifically on social networks, we would usually have as input a graph that represents the social connections between users. Think of Facebook, for example, and we would want to use this data to be able to predict user interest, to give them certain recommendations or show them certain ads that they might be interested in. This is just an example graph, example data set from the Snap Eco Facebook, just to give you a sense of how complex and large graphs can be. Another example is in the area of cheminformatics, and usually here we would have several small graphs, and each graph would represent a certain chemical compound, and we would want to perform graph classification to be able to identify or predict certain compound properties, such as toxicity or solubility. Again, this is just an example graph from the MUTAC dataset. So in summary, unlike regular structured data, graphs are able to capture complex relationships, and they can be extremely diverse in both shape and size. So next, how can we process graph data? Traditionally, there still is graph kernel methods. These are considered the first approach to machine learning from graph data. They mainly map the graph into feature spaces and then use the kernel function to measure the similarity between pairs of graphs. Nevertheless, there are a number of limitations with these methods. Mainly, the mapping function is deterministic rather than learnable, and the pairwise similarity calculation usually resulted in many computational bottlenecks. On the other hand, graph neural networks first became successful in 2016 when the graph convolution network was introduced. And it mainly introduced deep learning into the graph data realm, which, as you can imagine, revolutionized the processing of graph data. And unlike graph kernel method, GNNs are able to directly perform graph classification based on the extracted or learned graph representations. And they're now used in many applications such as the Amazon Alexa system and the YouTube recommendation system. And in summary, GNNs are much more efficient than graph kernel methods, and they're now widely leveraged in pretty much any application that processes graph data. So let's dive into how do GNNs operate. Their operation can be divided into three main stages, mainly input, aggregate, and combine. For the input, we would have an input graph which consists of several nodes. Each node would have its own node feature vector, and the nodes would be connected together using edges. Then the aggregate stage mainly wants to take each node and all of its neighbor nodes and take all these feature vectors and reduce them to a single feature vector. And we can do that using reduce functions such as summation, mean, or maximum. And then the combined state just performs a linear transformation, which is usually followed by a nonlinear activation function. So when talking about accelerating GNNs, there are, of course, a number of challenges. Mainly, graphs can be extremely irregular. In the same graph, you can have one node that's connected to only one other node, while another node in the same graph is connected to a million nodes. And this, in turn, dictates having varying memory access requirements as well. Graphs are also usually very sparse, which presents us with a set of both dense and sparse operations to deal with. Memory bandwidth is usually a major bottleneck since graphs can be huge. And finally, there are currently many existing and also developing GNN models, so the hardware or the software accelerating GNNs need to be flexible enough to accommodate this wide range. So let's focus on hardware acceleration in specific. There is a dire need for this now since the software advancements are progressing at a much higher rate than those on the hardware side. We do have general purpose processors such as CPUs and GPUs. However, these are not able to match the GNN requirements due to their unique structure. We do have, of course, also application-specific accelerators such as FPGAs and ASICs. However, the main issue here is that electronic accelerators are now facing many limitations. This is mainly as we are entering the post-Moore's law and linear scaling era, where increasing the number of transistors and technology scaling is no longer, we're seeing like diminishing performance improvements as can be seen from this graph. So in conclusion, we need to start thinking outside of the box and go beyond just conventional electronic chips. And this is why we are focusing on silicon photonics. So why silicon photonics? Photonics in general is now already used in many communication systems where we are seeing data being transmitted and processed with light. Even on the chip scale level, many startups and companies already started working on this. And silicon photonics allows us to implement both the electronic component and the optical components on a single chip, which is very beneficial. This results in having very high throughput since we are operating at the speed of light. Low energy values since we have the very high speeds and relatively low power consumption. And finally, as I will be explaining later on in the next slide, silicon photonics can be used to perform complex operations such as multiply and accumulates, which most of you probably know these are the main operations in neural networks in general. And in fact, using optical computations, we can perform, like when looking at single MAC, we can have up to 4 times in order of magnitude better latency. So in terms of the circuit and the different devices used in silicon photonics, we would usually first have a laser source that can be on-chip or off-chip. Then we would have a waveguide in which the optical signal traverses. And using wave division multiplexing, or WDM for short, we can multiplex several optical signals into a single waveguide, which is very helpful as you will see later on. Our main optical devices are the micro-ring resonators, or MR for short. These are optical modulators that can be used to perform the MAC and other operations as well using a tuning circuit. Then we have the DAC arrays that convert the parameter data to analog signals to tune the MR devices. Photodetectors then are able to detect the optical signals and convert them to analog values, which are then converted to the digital domain using ADCs. So now if we focus, like, how does an MR device operate? If we focus on the figure on the left, sorry, on the right, I guess. So we would have an MR device would have first an optical signal that has a specific transmission spectrum or a specific amplitude. And then as the signal goes through the MR device, its transmission spectrum will change. Specifically, its amplitude will be altered according to the tuning signal that was used with the MR to tune the MR device. And this is basically how we would encode or imprint the signal onto an optical signal. So how can we extend this to perform the MAC operations? If we look at this specific example for vector multiplication, we would need 2 separate sets of MR link arrays, and here each color of the MR indicates that it's configured to operate on a single wavelength. So what will happen, like we will have three optical signals, which will be multiplexed into a single waveguide using WDM as mentioned. And then as these signals go through the first MR, the value of A1 will be imprinted onto the first optical signal, then A2 onto the second optical signal, and so on. Then as these set of signals pass through the second MR link array, when another signal is imprinted again onto the same optical signal, we end up with a multiplication operation. And this is basically how we will end up with the three multiplication terms. What's left is just to add them, which can be done using the photodetectors. And as you can imagine, we can extend this to perform matrix multiplication by just having several rows of this or a similar configuration. So next, what if we want to perform addition operation, for example, which is also an important operation with GNNs? What we would do is we can use optical coherent summation. Here, the term coherent indicates that we're operating on a single wavelength, and we would have like a similar setup here, where the first laser source would generate a signal with the value of A1 imprinted onto it. Then the second laser source will generate a signal that will be split into the two arms. The first one will have the value of A2 imprinted onto it. So then as these two signals have the same wavelength, they will interfere, resulting in a summation operation. So we'll end up with A1 plus A2. Similarly, with the second arm, it will have the value of A3 imprinted onto the optical signal. Then again, these optical signals have the same wavelength. So when they meet, they will interfere again, and we will end up with A1 plus A2 plus A3. Just an example summation. However, there are, of course, challenges in silicon photonics, such as crosstalk noise and signal losses. However, I'll be talking later on about how we mitigate those. Which brings us to our main, or our proposed solution, which is GHOST. So the main contributions can be summarized as presenting the design of a novel GNN accelerator. In fact, this is the first GNN accelerator that uses silicon photonics and optical computations. It can accelerate multiple existing variants of GNN models. We conducted several detailed device, circuit, and architecture level optimizations to mitigate the various GNN and silicon photonics challenges. And we also conducted a detailed design space analysis and exploration to be able to find the optimal architecture configuration for our design. And finally, we did a comprehensive comparison with the TPU, CPU, GPU, and several state-of-the-art GNN accelerators. So just to give you a sense of the previous effort done in this area, in terms of the GNN accelerators, there is HiGCN, which is an electronic accelerator focused on graph convolution networks. Its architecture mainly was composed of two separate engines, one for the aggregation stage and one for the combination stage. We also have an engine which is an electronic accelerator as well for GNNs. It mainly had a unified architecture to perform both the aggregation and the combination stages. And then there is ReGNN, which is a bit different. It used ReRAM cells. So most of its computations were done in the analog domain. Nevertheless, all these prior works on electronic and ReRAM-based GNN accelerators have many limitations and challenges. If you remember, like we talked about the limitation with the Moore's law and Denner scaling, and also with ReRAM cells, there are a number of unique challenges such as high write energy and latencies. So in terms of photonic accelerators, there is Crosslight, which is a GNN accelerator. They had several engines to perform the map operations using MR link arrays. There's also RecLight, which focused on RNN acceleration. They also had engines to perform the map operations. They added devices using optical coherent summation, and most of their nonlinear activation functions were done in the optical domain as well. And finally, there is Tron, which is a transformer accelerator. It mainly focused on performing the complex transformer operations, such as the attention in the optical domain. using several cascaded MR bank arrays. Nevertheless, no prior work developed a photonic accelerator for the complex and diverse GNN workloads till we are presenting now GHOST. So this is an architectural overview. The main architecture is divided into three main blocks, namely aggregate, combine, and update. And each block has its own units. The shaded units are divided up into V processing lanes. At any point in time, each lane is processing a single node from the graph. Accordingly, at any point in time, GHOST will be processing V nodes at a time. And then we have edge control units. These are electronic units that are responsible to go fetch neighbor nodes and pass them to the gather units if they are neighbors of the nodes being processed. And this mechanism operates according to a graph partitioning algorithm that we're using, which significantly helps with the graph irregularity and sparsity challenges I talked about. So we focus first on the aggregation block. The main unit is the reduce unit. If you remember, this main operation with the aggregation is usually revolves around summation somehow. So we configured our architecture as our reduce unit as an optical coherence summation block, where each row is assigned one feature from the feature vectors, from the node feature vectors, and each column is assigned one neighbor node. And if you remember how optical coherence summation operates, all the signals in one row will be added together. And this configuration allows us to support various aggregate functions and thus GNN models, such as summation mean. And even for the maximum function, we just do a very small alteration where we would be using optical comparators as shown here. And then all these summed signals will be at the end combined together and passed directly to the transform units in the optical domain, which brings us to the combine and update blocks. So the main units in the combine is the transform unit. This unit performs the linear transformation using this MR bank array. And then most GNNs also do a batch normalization operation afterwards. So for that, we are using broadband MR devices. These are MR devices that are able to collectively tune all the signals in the waveguide. Then the activate unit in the update blocks performs the nonlinear activation. For this, we have two subblocks. First is for the SOA-based activation. SOA is an optical device that's able to amplify or de-amplify a signal according to its configuration. And a lot of previous work has shown how we can use this to perform several nonlinear functions such as ReLU, sigmoid, and pan-H. Then for other nonlinear functions that cannot be computed optically, we do have a configurable lookup table. Next, GHOST supports many optimizations for the orchestration and scheduling, as well as on the device and circuit levels. For the sake of time, I will not go through each one of them, but we can quickly touch upon a couple. So first, for the pipelining and scheduling, GHOST is able to efficiently adapt its execution pipeline according to the specific model being computed. So for example, graph attention networks on the left, they don't follow the regular execution order of reduce, transform, and update. Usually the reduce is done at the very end. So as you can see, GHOST efficiently handles the pipeline as needed. And we do pipelining on two granularities. First, on the within processing one V node group. If you remember, at any point in time, GHOST is processing V nodes at a time. So we pipeline the procedures as shown, and also we pipeline the operations between two different group nodes. Next, another optimization is the weight DAC sharing. This is based on the idea that in the transform units, when performing the linear transformation in GNNs, the weights are shared across all nodes in the same graph. Accordingly, we don't need separate sets of DAC arrays for each transform unit. We can just have one set of DAC array that converts the values to the analog domain to tune the MR devices at once. and then share these values across all transform units. This significantly reduces the energy. I don't think I mentioned this, but DACs are one of the main bottlenecks with the silicon photonic devices. So reducing their number reduces the energy. However, this would dictate that we would need all processing lanes to be operating in harmony, which can be managed. Another optimization on the device level is the MR device optimization. We use numerical tool to determine the optimal physical MR parameters as shown here. And we also did several design sweeps, one for the coherent MR bank design, which was used in our reduced units. This graph here shows, like, the red plane shows the cutoff SNR value, which is the least SNR acceptable value to ensure error-free computation. And we were able to determine, like, the maximum number of rings that can be put together on a single row without too much signal losses or crosstalk. And we similarly did another design sweep for the non-coherent MR bank design using our transform units. So in conclusion, these MR design optimizations significantly reduce the heterodyne, which is incoherent, and the homodyne coherent crosstalk. So next, for experimental setup, we designed an in-house Python simulator that performed both the software mapping for the graph data and the hardware mapping for all the electronic and optoelectronic devices used. And the buffers and memories, the costs were all estimated using Cacti tool. We focused on 4 GNN models, namely GCN, GraphSage, Graph Isomorphism, Graph Attention Networks. This table here just gives you a sense of the different data sets we did our experiments on, just to show you how different and large they can be. And we used 8-bit quantization based on our software experiments, and we did compare to several state-of-the-art GNN accelerators, as well as TPU, CPU, and GPU. So these are the results for first for the GOPS, or data operations per second, which is a throughput metric. Ghost efficiently outperformed all of the platforms we compared against, and it achieved at least 10.2 better GOPS values. And our power was only 18 watts, which is pretty average compared to other GNN state-of-the-art accelerators. It's even on the lower side. Then we have energy, the results for the energy per bit, which is an energy efficiency metric. Those also outperformed all other platforms, and it achieved at least 3.8 times lower EPD values. Okay, so in conclusion, we presented GHOST, which is the first silicon photonic accelerator for graph neural networks. GHOST can efficiently accelerate the inference of a very broad family of GNN models. The throughput improved by at least 10.2 times, and the energy per bit, or energy efficiency, improved by at least 3.8. Thank you.
Any questions from audience? Yep.
Thanks. Nice work. I just want to find out, how did you simulate a couple of things? The data came from DRAM, I presume, right? Or you had a picture with the DRAM on the side.
Yes.
So DRAM would be probably the limitation of your speed. Did you take that into account for speed calculations?
We did, yes. We using Cacti tool and DRAM sim, we modulated the communication with the DRAM and determined, like, the needed bandwidth. And this all was used in all of our calculations and simulations in our experiments.
And one other question, how did you convert the electronic data into photonic data and backwards? And how much energy does that take?
So to convert, okay, so to get the optical signals, we have the laser source which generates the optical signal. then we use the MR devices to imprint certain like GNN values onto the optical signals. And then these optical signals are converted to the digital or digital domain using the photodetectors and the ADCs.
But they were also simulated in your system?
Yes, they're all simulated.
And what sort of lasers did you use?
Mostly VCSEL units.
Pixels? Thanks.
Thank you much. I think we don't have more questions. Yeah, if you have more questions, please drop to by the poster. And thank you much again to the speaker. And now we have a video presentation for the work in progress paper for the first one. And for second work in progress paper, we are still missing the speaker.
Okay. Hello, everyone. My name is Xu Jinyu. I am pursuing my master's degree at Southeast University in Nanjing.
He's presenting himself. I don't need to read the bio. So that's fine. And then you can start, of course.
China. It is my honor to share my work with you, the title of which is Error Compensation-Based Energy Efficient MAC Unit for Convolutional Neural Networks. My presentation will include the following 4 parts, which are introduction and motivation, MAC unit design, experimental results, and the conclusion. First, let's talk about the introduction. With the development of process technology in recent decades, the performance of processors has developed tremendously. However, the rise of applications such as big data and artificial intelligence have raised higher requirements for energy-efficient computing units. At the same time, AI applications such as image classification and speech recognition are error resilient, so it is not always necessary to perform accurate operations when processing data. Therefore, approximate computing, which can achieve a balance between accuracy and energy consumption, is gaining popularity. The most universal artificial neural network is the convolutional neural network. The main computation of a CNN comes from the large amount of convolutional layers, so it is necessary to design an approximate MAC unit for CNN. A variety of circuit design methods based on automatic logic synthesis have been proposed in recent years, such as BMF and CGP. Using CGP to automatically generate approximate circuits is not efficient for circuits with too many nodes because of the large degree of freedom, while BMF is more suitable for the design of large-scale approximate circuits because it can reduce the time complexity by decomposing the input matrix into several subcircuits. For approximate adders, the structure is relatively simple, so they are easy to design with error bias in a specific direction. Therefore, the approximate multipliers are designed using BMF in the proposed approximate MAC units, and the approximate adders are produced by CGP according to error characteristics, thus making the errors compensate for each other. Besides, since the error in the less significant bits of the calculation has little impact on the results, a low-pass OR adder can be used for partial accumulation. Next, let me introduce the structure of the MAC unit we designed. The weights and activations of the neural network are quantized to 8 bits to reduce the computation complexity. We divide 8-bit signed input operands into 3 parts: the sign bit, the more significant bits, and the less significant bits. The sign bits of the input operands are used as the input of the XOR gate to obtain the sign of the output. The remaining 4 parts are multiplied and added to obtain the products, in which accurate calculation is adopted for more significant bits, while approximate calculation is adopted for less significant bits. The relative error distributions of the approximate multiplier and the MAC unit are shown in the figure, which indicates that the error is concentrated around 0 and close to symmetrical, so that the accuracy loss caused by approximate circuits can be compensated. The proposed MAC unit are evaluated on Silver 10 using ResNet 18. The accuracy of MAC units is shown in Table 1, It is clear that using EROA and CGP adders with BMF multipliers achieves the highest accuracy. The MAC unit is synthesized using 28 nanometer process, and the results show that the PDP is reduced by 58.8% compared with the accurate 8-bit MAC unit. The performance comparison of the proposed design and the previous works is shown in Table 2, proving that the design has achieved a significant improvement in energy efficiency and network accuracy. The last part is conclusion. In this work, we propose a MAC unit for CNN based on mutual error compensation of approximate multipliers and adders, thus making a trade-off between hardware overhead and network accuracy. That's all for my presentation. Thank you for your listening.
Hello, can you hear my voice? Hello? Sorry, I can't hear your voice.
Now you will get me. Okay.
Yes.
Okay. I'm sorry, my mic was switched off.
Okay.
I just mentioned that you couldn't make the travel due to visa restrictions.
Yes.
Thanks a lot for joining us. And do we have a question from the audience? Maybe I will have one. How flexible is your framework actually? Can you change the word width of your architecture in an easy way that you have at the end some kind of, let's say, trade-off between broad lengths and your error of your approximate computing architecture for your Mac?
I'm sorry, I can't hear you clearly. Can you say it again?
Make it short. I'm just talking about the word length of your approximate Mac device. Can you find the trade-off of your word length and the capabilities of your approximate Mac unit?
Are you talking about the trade-off?
Don't talk it. I did get
Is it about the trade-off between efficiency and hardware cost?
So but you don't consider the different word lengths in that sense. Okay.
In my design, we use approximate computing in the low bits of the multiplication and the accumulation, and we use accurate in the high bits. So in the high bits, they are in the low bits, we use approximate computation, so there are some errors that will be generated, but they don't affect the output. Have a very impressive influence on the output. So by using approximate in the low bits and accurate in the high bits, the trade-off between hardware overhead and accuracy is achieved.
Okay, thanks a lot. Any other questions? Yeah.
In the approximate MAC design, were the approximation applied on both the multiplier and the adder, or was the approximation applied only on the multiplier part?
Both approximation is adopted in multiplication and accumulation, but in the accumulation we use adders that are generated by CGP, and in the multiplication the approximate multipliers, they are generated by BMF. So there are two different algorithms.